Hello, this video is on finding volumes of solids of revolution. And what that means is that you take a region of area and then you revolve it about an axis of revolution. And by revolving it, you create a solid. And I'll show you an animation in a little while to see what we mean by that. But here's a function that I have, f, and we're looking at it from a to b. And you can create a region by finding the area from a to b. We know how to find the area, it's just the integral of f from a to b. That area creates a region, and then you take that region and you can revolve it about an axis of revolution. So this is more or less what a question would look like. You have a function f. It'll say something like revolve the region between f and the x-axis from x equal to a to x equal to b about the x-axis. And that's important that it says about the x-axis, because then that tells you how your revolution is going to go, and that determines everything else about the problem. So just to remind myself that I am revolving about the x-axis many times, I go to the whatever the axis of revolution is, and I write or draw a little loop just to remind myself that there will be a revolution about that axis. Now, how do we create the revolution? This is very important, and you have to visualize what's about to happen, and you have to be thinking in terms of 3 dimensions. Even though the pictures that I'm drawing are 2-dimensional, you have to use your imagination and visualize it in 3 dimensions. I'll try my best to draw it so you can see it. The first thing we do is we start the same way as the area problem. We start by drawing a representative rectangle. And that purple line is my representative rectangle. And this line is extremely thin, just like the representative rectangle. And the height of it is f. Whatever the y value happens to be at that point where I touch the function, that y value is the height of the representative rectangle. But then, to make it a solid, we take this rectangle and we rotate it about the x-axis, which is very hard to do on paper. But basically, this rectangle, pretend that it's coming out of the screen and it's rotating, but it's like a door hinge, and it's attached to the x-axis, so it cannot move on this end, but it can swivel itself along the x-axis. So then let me tell you what it's going to do. It's going to come out of the screen, then it's actually going to hit quadrant 4 as it swings about the x-axis, then it hits the screen again, then it goes through the screen, and it comes right back up from the other side. So then when it does that, it creates a little disc, and this is what that looks like then. Okay, so more or less something like this. Now, in reality, if you were looking at the disc, because you're staring right at the screen, you would not be able to see it as a disc. You would actually just see one line instead of the one blue line instead of the disc. But I have to draw it at an angle so you can see what it would look like. And this disc, it's got area, but because the rectangle, the purple rectangle, was actually very thin, it's got some thickness, but it's very small in thickness, then we could think of the disc as having volume, because there is some very small thickness that's part of the disc. So then, when you create this disc, you already have a piece of volume. Then what we're going to do is we're going to take that one disc and we are going to let it move from A to B, which means you're going to have an infinite number of little disks. Each one of those has very, very small amounts of volume, but they do have volume, and when you add them up, it creates the volume for the whole solid. And that's why the solid is called a solid of revolution, because it was created by taking a region and revolving it about an axis. So then let me tell you what else you have to visualize as part of the picture. I just took one rectangle, that purple rectangle, but in reality there's a whole bunch of them, because I could have gone to any piece of the function. I just chose this little section here. But there's also a disk over here, and there's a bigger disk at this end, and the smaller disk is on this end here at A. So infinitely many of them. So what happens really is that you get an image of this region down here. Okay? Let me see if I can draw that for you. Well, I tried my very best, and just pretend that this here is a reflection of the original function about the x-axis. And so you can see how the disk, as it revolves, it creates a solid. And it's very hard to see this in 3 dimensions, but in class we talked about functions like this. Some people said it looks like a volcano, you're just going to have to set it on its base. Some people said it looked like a tree stump. Some people said it looked like a speaker. I don't know. But basically, this is the method for creating solids. You take a region, you take a look at one representative rectangle, you let it swing about an axis, and when the rectangle swings, it creates one disk. And this disk has thickness, and then it's got volume, and then we take infinitely many of those disks, and that's how we create the entire volume of the solid. So let's see, let me try and show you another one of those disks. So there's another disk close to the right end of the region, and please just visualize that there are infinitely many of them from A to B. Each one of them infinitesimally thin, but with some volume. And so by adding them up, a whole bunch of them, you can actually get the volume of the solid. Now we're interested in, well, how do you find the volume of it? First, we start by saying, let's find the area of one of the disks. And because the disk is a circle, the area of the disk would be pi times radius squared. But then we have to think about, well, what's the radius of the disk? If you look at my picture, the radius is the purple line, right? And it's actually a rectangle, because remember, it's got some width, very small width. And so then what is that distance, the purple distance? Well, it goes from the x-axis all the way to the function f. So then the radius is just whatever y value the function has. From the x-axis to the function, that means that the radius is f of x. And this is important. So then the area of the disk is pi times whatever the function is squared. Okay? That's the area of one disk. Well, what about the volume then? What is the volume of one disk? Well, the volume is going to be the area of the face of the disk, but then times its width. Let me do this for you here and see if you can relate to the picture. So here I took one disk from the solid, and now I'm laying it on one of its faces so you can see it from a different perspective. And we're saying, how do you find the volume of one of those disks? Well, it's really a cylinder. And so how do you find the volume of a cylinder? You take the area of the base and then you multiply by the height. And so what is the height of this cylinder? Well, you can think of it as a height, but it's really just the thickness of the disk. And by looking at the picture, we know that this disk has a thickness dx, which means a very small amount. So let me come back here to my original picture. Right there, the thickness is called dx, a very small change in x. That's what dx represents. And so then the volume of one disk would be the area of the base, pi radius squared, and then that times the height, dx. So pi r squared dx. This is the volume of one little disk. What about the volume of the whole region? But for the whole region, you have to add up all infinitely many disks. And so then the conclusion to this is that the volume of the solid is given by the integral from a to b of pi, which is a constant, so I'm going to factor it out, times the radius, which is given by the function f squared times dx. And this is called the disk method. Let me bring it up here. This is the conclusion that we have right now. The volume of the solid revolved about the x-axis is pi times the integral from a to b of the radius, which is f of x, squared dx. Basically, you're saying it's the volume of a cylinder. And so then the integral adds up infinitely many disks from a to b. Now, you should be able to look at every single piece inside of that formula and make sure you can identify it based on the picture we drew. For instance, dx, you should be able to say, oh, that's the thickness of one of the disks. And it's being multiplied by f of x squared, which is radius squared. So when you do pi r squared, that's area of the base of one disk, and then times dx gives it volume, because this is the width or the height of one of those cylinders. And then the integral is just saying add up infinitely many of them. One thing I want to touch up on is, why is it f of x? Well, if you look up here at the picture again, this value is a, and so then what would you call the y at this point here? You would call it f of a. Now, where was my disk? My disk is at some random location. I don't know exactly. So then what we say is that the disk is at some x value. And then we would say, okay, so then what about the height at that point? What would it be? And the conclusion is, well, that should be f of x. If this is a here and this makes it f of a, then this random location x has a height f of x. And that's why the f of x goes right there. So we just want to make sure that we call this the disk method. Some people use a C or a K. I'm going to use letter K, disk method. And let me try an example coming up. So here's the first problem. They want us to find the volume of the solid generated by rotating the region bounded by e to the negative x, x equals -1, x equals 1, and the x-axis about the x-axis. So the first thing you have to do is make sure you can graph some of the basic functions like e to the x, ln of x, transformations of those, quadratics, some cubics, you should be able to graph quite a few of the basic graphs. And so there's e to the negative x, and x equal to -1 and x equal to 1, those are vertical lines. And the first thing you want to do is identify what is the region that is going to be bounded by these lines and graphs. And so here's the region from -1 to 1. That's going to be rotated about the x-axis. Also, let me go to the x-axis and then mark a symbol so that I know that the rotation happens here. So then the next thing I want to do is draw the discs, or at least one of the discs, so that I can set up the integral. Okay, so let me try and do that. So here you can see how I've drawn the discs that create the solid. One thing I want you to notice and to be very careful when you set up your own problems is that notice how my radius on the discs, the radius always goes from the axis of revolution to the original curve. It never goes to the reflection. This is the reflection here of the original function. The radius will always be drawn from the axis of revolution, which was the x-axis, up to the original function. Or if this had been the original function, then the radius would have come down here. Okay, so please pay attention to that because this radius is important because that's the radius that you get to plug in to the formula. Okay, so then hopefully you can see that a solid will be generated here. You only have to draw one of the discs. You don't have to have more than one. And if this is a free response question or multiple choice, no one's going to look at the picture. The picture doesn't gain you any points, and you don't lose any points because of the picture. But you do need the picture to be able to set up your integral. So it's just a visual aid for yourself. So now I'm going to start by saying, what is the area of one disk? Well, that is pi times the radius squared, because that's the area of a circle. But what is the radius? And this is a very important question. It's probably the most important concept here. The radius is the distance here, and so that would be the height of this function, which is e to the negative x, and so that's what the radius is, e to the negative x. And so then the area of the disk is pi times e to the negative x quantity squared. And so from there we can move on and say, let me just say that's the area of one disk. What about the volume of the disk? Well, volume is going to be exactly the same thing, pi r squared, but then you have to multiply by the width of it, or the thickness of it. And here you can see that the thickness is a horizontal distance, and we call that very small horizontal distance dx. So then the volume is pi e to the negative x to the second, that's like saying area of the base, times the height or the depth dx. Now this is just one disk. What about the volume of the solid? That will be pi times the integral from -1 to 1 of e to the negative x squared. Now if I actually take that, it'd be e to the negative 2x, because you multiply powers, times dx. And this is something you could integrate yourselves. I'm not going to go over the integration, but it's basically e to the same power divided by the derivative of the power. So it's going to be e to the negative 2x divided by negative 2. And then you evaluate from negative 1 to 1. And don't forget to bring down the pi. And whatever number we get from that, that is the exact volume of that solid of revolution. And the other thing you should understand very well is why the limits are negative 1 to 1. Because when we take the disks, they repeat, or they pile up from negative 1 to 1, and that's what creates the solid. Okay? So it's saying take disks from negative 1 to 1, or add up the disks from negative 1 to 1. And dx means your thickness is horizontal. It also means you are rotating about the x-axis. If you rotate about the y-axis, then this changes to dy, then your disks become horizontal, and the depth or the thickness of the disk becomes dy. And then this function would have to be solved for x, so that you have a function of y here times dy. And maybe later I get to show you an example of that. Okay. So the method we discussed earlier was called the disk method, and the method we're going to go over right now is called the washer method. And we use the washer method whenever the solid we are generating has an empty space or a hole through it. And that's one of the first things you want to be able to recognize from the problem. Do you have an entire solid, or when you do the rotations or the revolutions about the axis, are you going to end up with some empty space or a hole going through the object? So here's an example of a situation that requires the washer method. Notice we have the shaded area, and the region is bounded by the graph of f and the x-axis, and the line x equals 5. And we're trying to rotate it or revolve it about the line y equals 3. This is no longer a revolution about the x-axis, but about the line y equals 3. So let's picture what that would look like with disks. So many things are happening in this picture, and I want to really make sure that you understand exactly what's going on in the picture. First of all, notice this is my axis of revolution. So look at the way I drew the radii from the axis of revolution to the original function. This was the original function. This was the original region, and this is the reflection of that. Okay? So from the center, or from the axis of revolution down to the original function. And the second thing that's happening is I need two distinct disks. One of them, the larger one, this is the disk that'll actually give me volume, because it's going to cover everything from 2 to 5. Now notice, this disk is always going to go from the axis of revolution down to the x-axis. It doesn't actually hit the curve, it goes straight down to the x-axis. And when you do that, what it's basically going to do, it's going to create a cylinder. I hope you can picture that. It's just going to be a cylinder. And then the disk in the middle, the smaller one, this is actually going to create a hole right between the two reflections. Okay, so there is some empty space here. So you start with the big disk, which is basically just a cylinder, and then you carve out a hole right through it. And this is why we know we're going to use the washer method, because there will be a hole running through the solid. So now the setup is very similar to the disk method. You just have to take away the empty space. And so the way we set it up is we say volume equals pi times the integral from a to b of the big radius, that's why I'm using a capital R, as a function of x squared minus the little radius, that's why I'm using a lowercase r, as a function of x squared, and then all that times dx. Okay? And what this will do is that it'll take care of one big radius minus the other. So basically take the cylinder and then subtract the hole in the middle. And for this example here, now you have to figure out what is the big radius and what is the little radius. But as far as formulas go, this is the washer method. And one thing you want to make sure you don't do, see how every term is being squared. And some students, they like to simplify things, and many will say, oh, it's r of x minus little r of x quantity squared. And this is the number one mistake of people who get this wrong. You don't subtract and then square. You actually square individually. Please keep that in mind, or you're going to be one more of the statistics of students who miss it because they don't remember where the squares go. Okay, so then let me set up the problem. It's going to be, let's talk about the big radius. The big radius is the distance from here to there. And it doesn't matter where I place the disk, the big radius is always going to be the same distance. I hope you can see that. Okay? And what is that distance? Well, this is the line y equals 3, so then the big radius is always going to be 3. It's actually a constant. That's why we said we're just going to have a cylinder for that section. Now the little radius, that's a different story. The little radius goes from the same axis of revolution up to this function. So we have to think about, well, what do you call that distance, the blue distance? Well, it's going to be, one way to think of it is, let's think about the longer distance. The longer distance would be 3, and then you have to take away this little piece. That's not a 3, that's a bracket. And what is that height? Well, it's the function f, because isn't that the definition of the function, the height from the x-axis to that point on the curve? So then basically the blue distance is 3 take away f. 3 take away f, you end up with the blue line. Okay? So little r of x is 3 minus f of x. And that's something you're going to have to figure out independently. Every problem is different, and you're just going to have to recognize, oh, okay, it's the big distance take away the smaller distance. And it's always, yeah, big distance take away the small distance. Don't do it backwards. It's not f of x minus 3. It's 3 minus f of x. You can go back and think about when we were doing area. It's always top function minus bottom function. 3 minus f. And that's the blue radius. So now we have everything ready. We can set up the volume of the solid. And that's going to be volume equals pi times the integral from 2 to 5 of the big radius, which is 3, that was a constant, squared, minus the little radius, which is 3 minus f of x, and then that has to be squared. Oops. and then all that times dx. Okay? And of course we would have to work this out and figure out what is this function f, but right now I just want to make sure that we understand the setup. Please review this as many times as you have to understand why the radii are the way they are. So now I wanted to show you a video, an animation of how the washer method works with better visuals. And here we have two functions. I'm going to call the blue one f, and I'll call this brown one down here g. And you can see the area that's been shaded for you. That is the region. Also notice the axis of revolution. The axis of revolution is right there. And things are going to be revolved and you're going to get a solid out of this. And what I want to know is, well, how do I draw the disks? It's always going to be the same way, from the axis of revolution to the original functions. So this is going to require the washer method, because I can see that if I do a rotation here, then there's going to be some empty space at the end. That'll be a hole through the solid. But let me play the video for you. A few things to notice. These are the limits from A to B. You would have to find that intersection point. And this is the location X of some random disk. And there you can see the revolution about the axis. You can also see in a little while how the disk has the shape of a washer, like nuts and bolts and washers. And if you have infinitely many of them, see them moving, all infinitely many of them, that's how you get the solid. Hopefully you can also see the empty space in the middle. So then we want to know how would we set up that integral. We know it has to be the big radius minus the small radius. And so let's talk about that. What is the big radius? Well, just remember, the radius is always going to be from the axis of revolution to the original functions. And because there's empty space, first you want to make sure that the big radius gets all the possible volume. So then I would say the big radius has to go from here to there. And then you can have a disk like the one you see there. So the green line is my big radius. And what would you call that distance? Well, let's see. The axis of revolution is at 1, y equals 1. So then the distance from here all the way to the bottom, all the way to the x-axis would be 1. Except my big radius doesn't get to touch the x-axis. It stops at this function here. So then I would have to say the big radius is big distance 1, take away this little distance. And this little distance is the function g of x. So again, top function minus bottom function, 1 minus g. That's the green radius. And that's the big radius, 1 minus g of x. What about the little radius as a function of x? Well, first let's draw it. You can see it in the picture, you can see it here, that this is the hole, right? All of this, that blue little cone. And so then what's the radius of that disk right in the middle? Well, it's the distance from the axis of revolution to the original function. And then you could draw a disk right there. But what is that distance? It would have to be, again, the axis of revolution 1, but now I only get to touch this function, which was f. So the big distance is 1 all the way down to the x-axis, and then this distance here up to the blue function is f. So then the little radius would be top function 1 minus bottom function f. 1 minus f. 1 minus f. And I'm just really hoping that you can see why that works the way it does. Okay? So then the volume would equal pi, because that's a constant, times the integral from a to b. In this case it's capital A and capital B. The big radius, 1 minus g of x, that quantity squared, minus 1 minus f of x, that quantity squared, and then all that times dx. And I really hope that the video helped, and I hope that this last animation helps you see it better. This is called the washer method. Anytime you have a solid and there's some empty space that needs to be subtracted. When I see you on Monday, I'll be assigning some homework from the AP packet that has the volume questions, and the AP packet itself is labeled volume. So start working on those questions, and I will select several from the packet, and then you'll have to turn it in for homework. But you don't want to wait till Monday to start working on it. I would start working on it now. And I'll see you in class Monday. Thank you.